we've arrived at a strange moment in our history. Right now, at this very second, metal robots on wheels are crawling across the rust-colored dust of Mars. A spacecraft built by human hands was deliberately swallowed by the storms of Saturn, and cameras we designed captured the frozen plains of Pluto from less than 13,000 kilometers away after a crossing of more than 9 years through absolute nothingness. From the outside, it looks like we've mastered space. It looks like crossing the void has become as ordinary as catching a flight between two cities. But that sense of mastery is a comfortable lie. We move with ease in one direction, and we hit a wall completely in another. There is a path in the sky that, in theory, should be the cheapest and the most obvious of them all. A place that is, in a sense, right there. And yet it remains one of the most impossible destinations engineering has ever faced. I'm talking about going up, about abandoning the flat tray where all the planets slide in their circles, and facing the sun not from the side, the way we always have, but from above or below, the top and the bottom of the solar system, the vertical axis. At first glance, it sounds absurdly easy. If you want to leave a spinning plate, you just point the rocket upward and fire the engines, right? This is where the universe smiles at us cruelly. The laws of physics don't just make this trip harder, they practically forbid it. Over the next few minutes, you'll discover why escaping upward costs almost 10 times more than going to Pluto, what actually exists in that never-photographed region, and the insane maneuver engineers invented to break through that wall. A plan in which, in order to climb, a probe first has to plunge straight toward the sun itself. Before anything else, you need to accept an uncomfortable truth about yourself. At this moment, whether you're sitting or lying down without moving a single muscle, you are traveling at a brutal speed. Earth doesn't float still in space. It races around the sun at roughly 30 kilometers per second. Put in more familiar terms, that's more than 100,000 kilometers per hour. And here lies the detail that changes everything. Every rocket that lifts off, whether from Florida, the steppes of Kazakhstan, or any other point on the planet, is already born carrying that sideways velocity as a gift. It leaves the launch pad inheriting those 30 kilometers per second, pushing it to the side. For most missions, this is a blessing. When we want to reach Mars or Jupiter, that lateral push does almost all of the heavy lifting on its own. It's like jumping off a spinning carousel. You're already flung outward with speed to spare. All you need is a small extra nudge in the right direction, just a few kilometers per second, and the probe slips onto a course for another world. Now picture the entire solar system as a giant vinyl record spinning slowly. The planets are tiny ants walking across that record. Traveling from one planet to another is like an ant walking toward the edge. Difficult, but natural. But going up is another story entirely. To escape the plane for good, perpendicular to absolutely everything, you first have to cancel out those 30 kilometers per second you're already carrying. You have to burn a mountain of fuel just to hold still relative to the sun in the horizontal direction. And only then can you begin to gain altitude. Engineers measure this cost with a number called delta V, which represents the total change in velocity a maneuver demands. Compare the two. Leaving Earth's orbit to reach Mars asks for something around 4 kilometers per second. Aiming straight up, out of the disk, demands nearly 30. That's almost 8 times more change in velocity for a trip that, on the map, looks so much shorter. This is our secret cage. Earth's spin hands us free tickets to cross the disk in every direction, but it raises impassable walls the instant we try to escape it. And that's why an absurd truth holds. Spending energy to touch a point a few million kilometers above the sun's pole is far more expensive than covering the billions of kilometers that separate us from Pluto. Because this vertical escape is so expensive, almost no spacecraft in all of human history has actually attempted it. And that produces an almost embarrassing fact. Here, in the year 2026, the regions directly above and below the sun remain our least known territory of all. Stop and think about the scale of that irony. We have maps of Mars so detailed we can choose which crater to land in. We know the volcanoes and hidden oceans of Jupiter's moons. We've photographed rings, comets, and asteroids the size of stadiums. But the poles of our own star, the one that warms your face and keeps everything alive, have barely been seen face to face. And this is far from a matter of vanity. It's a matter of safety. The polar zones of the sun are the stage for the most violent events it produces. That's where the fastest, most furious solar wind is fired off. That's where the star's magnetic field decides to turn itself completely upside down, roughly every 11 years, flipping the poles entirely. That process reaches directly into our lives. It interferes with satellites, with radio communications, and even with the stability of the power grids down here. The problem is that, to this day, we've observed the sun almost entirely in profile, always from around its waist. It's like trying to understand the weather of an entire planet while standing only on the equator, never once glimpsing what's happening at the icy poles. We believe we know the sun, but we've always looked at it from the laziest angle possible. In the entire history of space exploration, only 2 missions have managed any kind of privileged view over the solar poles. 2 across decades of attempts. The first was called Ulysses, launched all the way back in 1990, a partnership between the American and European agencies. To escape the tyranny of the plane, it used a brilliant and rather absurd trick. Instead of climbing by brute force, it first traveled all the way out to Jupiter and used the giant planet's colossal gravity as a slingshot, which hurled it out of the disk at a very steep angle. It was ingenious, and it gave us precious data. But Ulysses carried a serious limitation. It was 1980s technology. It had no cameras capable of handing us real portraits of the poles. It could only feel its surroundings, sensing particles and magnetic fields like someone reading a dark room with nothing but their hands. The second witness is at work right now as you watch. It's called Solar Orbiter, launched in 2020. Instead of a single violent throw, it has been using the gravity of Venus in repeated passes to tilt its own orbit little by little, patiently. And then, in March of 2025, something happened that will end up in the textbooks. Solar Orbiter transmitted the first direct images of the sun's south pole. What appeared on the screen was neither calm nor orderly. It was total magnetic chaos, a scrambled, twisted landscape that had almost nothing to do with the more well-behaved surface we always saw from the side. It confirmed a disturbing suspicion. The top and the bottom of our star are, in practice, entirely different worlds from what we had imagined, and we've only just begun to decipher them. But it isn't only the sun that keeps secrets along the vertical. There's an even bigger doubt about the shape of everything we call home. The sun constantly blows out a steady wind of electrically charged particles. That breath spreads in every direction and inflates a gigantic protective bubble around the whole solar system, a structure known as the heliosphere. It's inside this bubble that Earth and all the planets sail, and it is vital. It works as a shield, blocking much of the deadly cosmic radiation that streams across the galaxy. For a long time, textbooks taught us that this bubble had an elegant shape, something like a comet, a rounded front aimed in the direction of travel, and an enormous stretched-out tail trailing behind as the sun journeys through the Milky Way. It was a reasonable idea, almost poetic. But around the year 2020, researchers poring over data from American space missions reached a conclusion that shook the scientific community. The heliosphere may be nothing like a comet. According to those models, it would look more like a crushed croissant, a lopsided, strange shape, with 2 short arms and none of that long tail everyone used to draw. And why are we still arguing over this, with no definitive answer? For the same reason as always. We've never launched a probe high enough to leave the structure and photograph it from the outside. The legendary Voyager probes did cross the boundary of this bubble, but they escaped out the edges, never climbing high enough to photograph it from above, looking down. It's like trying to guess the shape of an entire house while peering only through the keyhole of the front door. Until someone truly rises and looks down, we'll go on living inside a structure without knowing its true outline. So how do you solve a problem like this? If you can't build a rocket with infinite fuel, how do you defeat the 30 kilometers per second that Earth forces upon you? The answer proposed by trajectory specialists is so counterintuitive, it sounds like cheap science fiction. It leans on something called the Oberth effect, and the maneuver works against everything intuition demands. Instead of pointing the probe upward and fighting gravity, you do the exact opposite. You throw the craft toward the sun and let it fall. As it plunges down into the sun's gravity well, the probe accelerates monstrously. At the point of closest approach, what scientists call perihelion, it can be traveling at hundreds of kilometers per second. And it's precisely in that instant of maximum speed, with everything working in its favor, that the engines are fired. The principle behind this was worked out by the pioneer Hermann Oberth, all the way back in 1929. The idea is that a rocket engine yields far more useful energy when it burns at extremely high speed, plunged into an intense gravitational field. The same fuel produces a much bigger payoff. It's like pushing someone on a swing at exactly the lowest point of the arc. The same effort transforms into an enormous boost. By firing the engines at perihelion, the probe absorbs so much energy that it can finally cancel its sideways motion and launch itself toward the vertical. The dive into the solar inferno becomes the ramp that points to the top of the universe. And there's a second technology that promises to help with this feat: solar sails. Picture immense reflective sheets, kilometers wide, that don't burn a single drop of fuel. Instead, they move on nothing but the soft, tireless pressure of the sun's own light pressing against them. They're slow. They may take years to tilt a spacecraft's orbit, but they never stop and never tire. Many engineers believe the marriage of the two ideas, a solar sail to close in gradually, and an Oberth-style dive for the final shot, will be the key that finally opens the door to the vertical axis. And if one day we truly pull off this feat, what would a probe see from up there? The first surprise would be the cleanliness. The plane where Earth lives is a dirty place. Over billions of years, comets and asteroid collisions have left a thin veil of dust spread across the whole disk. You can notice that dust from right here. On very dark nights, it reflects sunlight and forms a soft glow known as the zodiacal light. A probe climbing vertically would leave that haze behind within a few months. Up there, space is clearer, sharper. It would be the ideal spot for telescopes hunting for signs of life around other stars, free of the dust in our own backyard. The second revelation would be the sun shown without disguise. Instead of the churning plasma that dominates the equatorial region, the probe would plunge into the clean, fast flow of solar wind pouring straight out of the poles, feeling the star as it truly is. And finally would come the greatest prize of all, the great photograph. For the first time, we would look down and take in the entire solar system as a perfect disk. We'd see the rings of dust, the orbits of the planets drawn as concentric circles, and, in the background, the true silhouette of the heliosphere wrapping around us. That's the portrait still missing from humanity's album. We've already seen Earth suspended in the dark of space. We've already glimpsed the hidden side of the moon. But never, not even once, have we gazed upon our home seen from above. Exploring what lies above and below us is the next great leap in space exploration. It's the moment we'll stop being creatures trapped and crawling across a flat disk and finally become true three-dimensional navigators of the cosmos. So what would you bet on? The silent patience of solar sails or the madness of the plunge toward the sun? Drop your answer in the comments. If this journey moved you, leave a like, subscribe to the channel, and share the video with anyone who spends their nights looking up at the stars. Thanks for the company, and until the next voyage.